Hi guys, welcome to ENS181 Engineering Mathematics. So in this video, we're going to discuss method on finding the solution of a first order differential equations. Specifically, the not exact equations. So given a differential expression of mxy dx plus nxy dy is not exact if the test of exactness fail. So we are given the differential form of our differential equation mxy dx plus nxy dy equals to 0. So it is said to be not exact equation if the expression on the left hand side is not exact differential. So we try to do the test of exactness and it does not satisfy our test of exactness. So how are we going to solve this kind of differential equation? So we have to transform it to become an exact equation. By how? By multiplying an unknown function integrating factor. So we have to find this unknown function, this integrating factor, and when we multiply it to our differential equation, this one becomes exact. So the method of solution for not exact, we have two cases here. So case 1, if the integrating factor is purely function of x. So we have the integrating factor I, which is I of x. So if it is purely function of x, then there exists this function g of x, which is equal to partial derivative of m with respect to y minus partial derivative of n with respect to x divided by n. Then, if this equation is true, it means that g of x is purely a function of x, then we can use this formula for our integrating factor. I equals to e raised to integral of g of x dx. So after finding our integrating factor I, we have to multiply it to our original given differential equation to transform it to become an exact equation. And then we solve the solution using the method for exact first order ODE, which we already discussed from the previous video. Then case 2, if our integrating factor is purely a function of y. So we have this I, integrating factor I equals to I of y. So if our integrating factor is purely a function of y, then there exists this function h of y, which is equal to partial derivative of n with respect to x minus partial derivative of m with respect to y divided by m. So if this satisfies that h of y is purely a function of y, then we can use this formula for our integrating factor I, which is equal to e raised to integral of h of y dy. So after finding the integrating factor I, we have to multiply it back to our original given differential equation to transform it to become exact equation. And then we solve the solution using the method for exact first order ODE. So we have to check first which case satisfied in our differential equation. Is it case 1 or case 2? So we have an example here. We are going to find a solution for this differential equation dy over dx plus 3xy squared plus 2y over 2x squared y plus x equals to 0. So if you notice, this one is not in the differential form. So we have to transform it first to differential form so that it is easy for us to identify which are the mxy and nxy. So we rearrange this. We have 3xy squared plus 2y dx plus quantity 2x squared y plus x dy equals to 0. So first we're going to check the test of exactness, if this differential equation is exact or not. So we have partial derivative of m with respect to y must be equal to partial derivative of n with respect to x. So, based on this differential form, the value of our m is this 1, and the value of our n is this 1. So, we're going to partial differentiate this with respect to y. So, we have 6x y plus 2 equals to partial derivative of this one with respect to x. So we have 4xy plus 1. So the left and the right hand side are not equal, so it means it is a not exact differential equation. So we have to find the unknown function, the integrating factor I, to transform it to exact differential equation. So we have for case 1, if our integrating factor is purely a function of x. So we have g of x equals to partial derivative of m with respect to y minus partial derivative of n with respect to x divided by n. So we substitute the value. This one is just equal to 6xy plus 2 minus partial derivative of n with respect to x is 4xy plus 1. Then divided by the value of our n is 2x squared y plus x. Then we simplify this one. We have 2xy plus 1 divided by, we can factor out x. What's left is 2xy plus 1. So we can cancel the 2xy plus 1. So our g of x is equal to 1 over x. So this one is true for our case number 1. So we can use the formula for our integrating factor I equals to e raised to integral of g of x dx. So our integrating factor will become e raised to integral of 1 over x dx. We have e raised to ln of x. So the integrating factor I of x now is just equal to x. So we didn't proceed for using case 2 since case 1 is already satisfied. Our integrating factor is purely a function of x. So we can use this integrating factor I, which is equal to x, and we multiply it back to our original differential equation. So we have our integrating factor I of x equals to x. So we have to multiply it to our original differential equation, which is 3x y squared plus 2y dx plus quantity 2x squared y plus x dy equals to 0. So we distribute this x to the entire equation. We have 3x squared y squared plus 2xy dx plus 2x cubed y plus x squared dy equals to 0. So this one is our new differential equation after multiplying our integrating function. So now we have to check if this is exact. So we are going to use the test of exactness. So partial derivative of m with respect to y equals to partial derivative of n with respect to x. So we differentiate this one with respect to y, we have 6x squared y plus 2x. Then we differentiate this one with respect to x, we have 6x squared y plus 2x. So the test of exactness satisfied, so this new differential equation becomes an exactDE. So we can use the method for finding the solution for exact differential equation. So we can use the assumption partial derivative of fxy with respect to x equals to m, and partial derivative of fxy with respect to y equals to n. So we can use either of these two. So we are going to start to use this assumption. So partial derivative of fxy with respect to y equals to n, which is this one. From our new differential equation, we have 2x cubed y plus x squared. So we cross multiply the dy, we have fxy equals to 2x cubed y plus x squared dy. So we can now integrate both sides. So our solution f of xy is just equal to integral of 2x cubed y dy is x cubed y squared plus integral of x squared dy is x squared y plus h of x. So to find the value of this h of x, we're going to use this first assumption. So we are going to partial differentiate this with respect to x. So partial derivative of fxy with respect to x. Then we also partial derivative this one with respect to x. Our x cubed y squared plus x squared y plus h of x. So this partial derivative of fxy with respect to x is just equal to m. So we can equate this one with 3x squared y plus 2xy. Then we partial differentiate this one with respect to x. We have 3x squared y squared plus 2xy plus d of h of x over dx. So simplifying this one, cancel si 3x squared y squared, cancel din si 2xy. So what's left is dh of x over dx equals to 0. So finding for h of x, this one becomes d of h of x equals to 0. We integrate both sides, so our h of x is just equal to 0. So we substitute this back to our solution f of xy. So we have x cubed y squared plus x squared y. Then value ng ating h of x is 0. So hindi na natin siya isulat. So we equate this one with constant of integration or our arbitrary constant c. So this is the solution for the given not exact differential equation. So we have x cubed y squared plus x squared y equals to c. So we have another example here. We're going to find a solution for this differential equation xy dx plus quantity 2x squared plus 3y squared minus 20 dy equals to 0. So it is on the differential form. So this one is our m and this is our n. So we can now apply our test of exactness. So partial derivative of m with respect to y equals to partial derivative of n with respect to x. So this one is just equal to x. Then partial derivative of this with respect to x is 4 x. So this is not equal, so it means the given differential equation is not exact. So we're going to find the integrating factor I so that this differential equation becomes exact equation. So first, we're going to try the case 1 where I is purely function of x. So our g of x is equal to partial derivative of m with respect to y minus partial derivative of n with respect to x divided by n. So this is x minus 4x divided by our n is 2x squared plus 3y squared minus 20. So this is our g of x. So if you notice, it is not purely a function of x. So this does not satisfy the case number 1. So we cannot use this case number 1. We are going to try case number 2, where our integrating factor is purely function of y. So we have h of y equals to partial derivative of n with respect to x minus partial derivative of m with respect to y divided by m. So we substitute. So this one is 4x minus x divided by our m is xy. So we simplify this one, cancel the x. What's left is 3 over y. So our h of y is equal to 3 over y, which is purely function of y. So this one satisfy our case number 2. So then we can use our integrating factor I equals to e raised to integral of h of y dy. So this one is e raised to integral of 3 over y dy. So we have e raised to 3 ln of y. Simplifying this integrating factor, we'll get y cubed. So this is our integrating factor that we are going to multiply to our differential equation. So we multiply y cubed with our differential equation xy dx plus quantity 2x squared plus 3y squared minus 20 dy equals to 0. So our new differential equation now becomes xy to the 4 dx plus quantity 2x squared y cubed plus 3y to the 5 minus 20 y cubed dy equals to 0. So this one is our new differential equation. So our new differential equation now becomes xy to the 4th dx plus quantity 2x squared y cubed plus 3y to the 5 minus 20y cubed dy equals to 0. So we can apply now our test of exactness. So we have partial derivative of m with respect to y equals to partial derivative of n with respect to x. So the left hand side of this equation is 4x y cubed. Then the right hand side is 4x y cubed. So both sides of the equations are equal, so the test of exactness satisfies. So this new differential equation, after multiplying the integrating factor, becomes exactDE. Then we can apply the assumption partial derivative of f of xy with respect to x equals to m, and partial derivative of f of xy with respect to y equals to n. So we're going to use this one first. So partial derivative of f of xy with respect to x equals to m, which is xy to the fourth. So we cross multiply this dx, we have d of xy equals to xy to the 4 dx. Then we can now integrate both sides. We have our f of xy equals to 1/2 x squared y to the 4th plus g of y. So to find the value of g of y, we're going to use this second assumption. We're going to partial differentiate this equation with respect to y. So partial derivative of 1/2 x squared y to the 4th plus g of y with respect to y. So this part of the equation is just equal to n, so we can equate this one with 2x squared y cubed plus 3y to the 5 minus 20y cubed. Then the partial derivative of the right hand side is just equal to 2x squared y cubed plus d of g of y over dy. So simplifying this equation, cancels it, 2x squared y cubed. So what's left is dgy over dy equals to 3 to the 5th minus 20y cubed. So we cross multiply dy, this one becomes d of gy equals to 3y to the 5 minus 20y cubed dy. So we can now integrate both sides. So we have g of y equals to integral of 3y to the 5 is 1/2 y to the 6 minus integral of 20y cubed dy is 5y to the 4th. So we can now substitute this gy back to our solution f of xy. So our solution now becomes 1/2 x squared y to the 4th plus the value of our gy is 1/2 y to the 6 minus 5 y to the 4th equals to our arbitrary constant c. So this one is the solution for the given not exact differential equation. So in this part, we have the practice quiz. So we are going to find a solution for the given not exact first order ODE. So I want you to pause this video and try solving the solution for this one. So the answer for this practice quiz will be posted on a different video. So that's it for first order differential equation, solution for not exact differential equation. So I hope you learned from this video. So our next topic will be homogeneous first order ODE. See you on the next discussion.